And welcome back to a new video on boundaries, and this time again we'll do an example of a river coming off of a canyon in a mountain range. So here are a few pictures to motivate this example a little bit. So here on the top left we have what are called talus basically, and these are, you can see these are just cones of stones or rocks, boulders, any sediment shedding from these sharp faces here, right? So you really clearly have these sort of almost like a delta shape, right? And again, these are essentially erosion from sharp slopes. Now, if you tilt that a little bit, right, you get what we call alluvial fans, and you can see here these are really water derived. So again, the talus are essentially like gravity derived, like it's just like rocks that sheds from these cliffs. Here on the right hand side is clearly water, like streams are really moving that sediment out of those canyon. And you can see here the alluvial fan is really what when the stream comes out of that canyon, then it just leaves that sediment there and keeps on going on its way. Okay, another example here we can kind of see the current channel here, right, coming off of that canyon and then coming out of here. Obviously those channels over time kind of move left and right and leave the alluvial in that typical fan shape. Okay, so some of these shapes sometimes are called wine glass canyon because they when you sketch them, they sort of look like a wine glass, I guess. So that would be the canyon or the valley where that stream is taking its water when it rains, and then the sediment, and then this is the fan, the alluvial fan at the exit. Now let's say we wanted to put a pumping well right somewhere. It doesn't have to be in the fan, but somewhere outside of that mountain range, right, in that alluvial valley someplace, right? It could be here, it could be somewhere further, it doesn't really matter, just somewhere outside of that mountain range. Well, now we have that mountain range here, right, which acts as a no-flux boundary, if you will. That's just an outcrop of hard rock, typically. Could be sedimentary rock, but the point is very low conductivity, right? Not, it's basically a no-flux boundary. So now we have an interesting system where we have a recharge boundary, which is the stream, and we have a no-flux boundary, which is the mountain, right? So the question is, okay, well, how do we represent this with our little, with our simple setup of these imaginary wells to represent boundaries, right? So now we have recharge boundaries and no-flux boundaries. How do we deal with those? Well, we deal with them very simply, like we've done before, essentially. So again, this is a sketch, an even more schematic sketch of the system, where we have our pumping well here at the bottom, which is a distance A from the mountain range. Again, remember that this is the no-flux boundary here. So we're distance A from the mountain range, a distance B from that river, from that constant head boundary, and now we need to account for them. So of course we're going to put an image across from that no-flux boundary to represent the mountain range, and we're going to put an image across from the river to represent that constant head boundary at the river. But now we also need to add a third image across that corner, because of course our image 1 here, right, is going to take water off of our river, and that doesn't work. So now we need another image to compensate for this. Same thing with our image 3 here. Our image 3 is going to put water into that river, right, to put water into our domain to compensate for the pumping, or to compensate for the constant head boundary, to compensate for that stream here. But now we have a problem with this one, so we need that image here, to counter the effect of our image 3 well. So again, we need images across from the boundary, but also across from that corner, basically, so that the system is complete, okay? So now, how can we represent this? Well, very simply, this is, again, our unconfined aquifer equation, right? So h squared equals the h r, which is, big R is our radius of influence, right? So it's the distance to the head, the initial head, if you will, or the head of the undisturbed system. Again, HR, and then we have Q over pi k. So this is always the same for the unconfined case. And then natural log of, so now we have the radius of the real well, okay, R for real, divided again by the radius of influence, so the undisturbed distance. And then the imaginary one, so again, you have a little reminder here of what they do, right? So the imaginary well 1 is here, and then the sign is always opposite what it does. So this well is pumping water, so it has a minus sign, plus sign, excuse me, right? And those two wells are across from the recharge boundary, so they're putting water in, so they have the minus sign with them, so minus and minus here. And again, imaginary 2, imaginary 1. So imaginary 2 here, imaginary 3 here. And this is it. So once you have all those, you can just like sum them all up like we just did. And once you have them all summed up, you can realize that this just simplifies again because the natural log of the sums, right, they're just products. So the radius of influence disappears from all those equations, and we end up with a very simple equation where we have the imaginary 1, this one because it has the plus is on top, and imaginary 2 and 3 because they have the minuses are at the bottom. So a very simple equation in the end, and then we can just solve that problem. Now we can see that because we're at a distance A from that mountain range and B from the river, we can write the distance, right, of the imaginary wells as 2a and so on and so forth, so just by geometry. And finally plug everything in our original equation, so we can see that this is equivalent basically to that simple equation with the natural log of some r radius of influence, which is not a radius of influence anymore, it's just that number here that combines all the geometry of all our wells. Okay, so again, we end up with a very simple equation where we can just use all that geometry and put it in our equation here. And that's how you solve this problem with the 3 imaginary wells. Thank you.